Okay.
Okay, so it's a great pleasure to have Carolina, who will tell us about real-world amplitudes from curves and surfaces. Yeah, please.
Okay, thank you so much. It's a great pleasure to give this talk. So today I'm going to tell you about this set of results that has been coming out since the beginning of the year of work together with Nima, Chi, Jin, and Song that all really come about as a consequence of this new way of thinking about amplitudes as coming from a problem about curves on surfaces. So this is what goes by the name of the curve integral formalism, which I'll start by briefly reviewing in the beginning of my talk. That gives us a way to talk about these stringy trace phi cubed formulas, which at low energies just give us trace phi cubed amplitudes. And then I'll proceed to explain how this formulation gives us access to qualitatively new features about the amplitudes. I'll start with this interesting kinematic connection between seemingly different theories, trace phi cube theory, the nonlinear sigma model, and Yang-Mills theory. Then I'll proceed to this new pattern of factorizations away from poles associated to some zeros of the amplitudes that Shruti already talked about yesterday. And I'll end explaining how this formulation gives us access to what I'll call perfect integrands for these theories. Okay, so the curve integral formalism at low energies gives us amplitudes of this trace phi cube theory, which is a very simple theory of colored scalars that interact via a cubic interaction. The amplitudes are extremely simple. Already at tree level, from the moment that we fix the color ordering of the external particles, we only get contributions from planar diagrams, which here are some examples at 4 and 5 points. And the point that I would like to highlight is that the momentum that goes through the propagators in these diagrams always corresponds to sums of consecutive momentum, so that the singularities are always when invariants of this type go on shell. So sums of adjacent momentum go on shell. So what I want to tell you now is that we can actually nicely label these sort of kinematic invariants that are associated to singularities by associating them to curves on surfaces. So already at tree level, if we consider the disk, and we assign a momentum to each boundary component of the disk, as I did here, then I take a curve on the disk that I'm going to call x15, and I can associate a kinematic invariant to this curve by homology. So this curve x15 can be deformed into this boundary curve whose momentum is just a sum of the momentum of the boundary curves. And so this xc that I associate to the curve c is precisely one of these invariants that appears as singularities on the amplitude. And so if I write the trace phi cubed amplitudes in terms of these variables, I make manifest the location of the poles. So exactly the same story goes through at loop level. Here I have the example of the punctured disk, where now to form a basis of homology on top of giving momentum to the boundary components of the disk, I also need to give momentum to one of these curves that ends on the puncture, which is associated to the loop momentum. But from the moment that I do this, any other curve that I draw on the surface, I can once more read off its momentum just by homology. So for this curve x5p, I can deform it into some boundary curves plus the loop momentum curve and read off its momentum. And once more, these xc's are precisely the variables that appear in the propagators in Feynman diagrams, so I can just write the amplitudes exclusively in terms of these variables. Okay, so in this language, Feynman diagrams is just what we get by considering full triangulations of the surface, which we already heard from Bernd in the morning as well. So here's an example at 5 points tree level, where I divide the disk into 3 different triangles by plunking down 2 curves, which are precisely dual to the 2 propagators entering in this diagram. And similarly, here we have an example at 4.1 loop, where I show the triangulation that gives me the contribution of the box diagram. So in this language, the amplitude is just what we get when we sum over all the possible ways of triangulating the surface. So here's 2 other examples at 4.1 loop. But the point that I want to emphasize is that when I consider these triangulations, it's crucial that I keep all the curves up to homotopy. So here's an example that makes this point manifest. It's crucial that curves x24 is different than curve x42, as they correspond to different propagators in the diagram, even though they are homologous to each other, so they have the same momentum. But as curves on the surface, they are different. This is going to be important a little bit later. And so what this curve integral gives us when we extract the low energy limit, as I'll explain, is precisely what we get by summing over all the ways of triangulating the surface. So Nima already talked about this in the previous meeting, so I'll be quite brief describing the formalism. But the star of the show is this so-called u variable. So to each curve on the surface, we associate a u variable, which is a function of these positive coordinates y's, is a ratio of polynomials in the y's. And this particular parameterization can be very nicely read off from a counting problem associated to the curve on the surface. But the sort of output of this formalism is that we can write the amplitude in this integral form, where we have an integration measure in the y's, which is just a simple d log form. And then we have this factor over here, which is the product over all the curves on the surface of their u variables raised to the power of alpha prime times the kinematic invariant xc. Okay, so at tree level, we can actually just match to these two standard string theory formulas. So Bern also already talked about this formula today. So this is the standard Park-Taylor worldsheet integral. So here's the Kober-Nielsen factor that in this language gets replaced with the product over the uij's to the alpha prime xij. So already here we see that in this formalism, we make manifest the dependence on the variables that are naturally associated to the location of the poles. And so the integral will develop a singularity, in this case, in the location where the respective uij goes to 0. And as for the integration measure, it just gets replaced by this logarithmic form in the y's, which automatically blows up all the singularities for you. So this is associated with the fact that in this representation, we don't need to gauge fix the worldsheet symmetry, and consequently, we can extract the field theory limit very easily. So at loop level, everything goes through exactly the same way. We have exactly the same formula, but the difference is that from the moment that we have the puncture in our surface, there are now an infinite number of curves that we can draw, coming from the fact that we can consider curves that self-intersect an arbitrary number of times as they loop around the puncture. So in this product over here, I have a genuine infinite product over these self-intersecting curves, and this is crucial to actually match the result that you get from bosonic string theory at one loop. But already here, what I'd like to point out is that if you only care about what's happening at low energies and you're using these objects to basically unify all the diagrams together, you can actually start with a much simpler object where you throw away this complicated infinite product. It turns out that this completely agrees at low energies. These infinite self-intersecting curves actually don't contribute at low energies. So you start with a much simpler object that agrees at low energies. Of course, it defines a different stringy UV regularization, which is not string theory, but it's still completely fine to define the low energy theory. Okay, so the last point I want to make about this formalism is explain how the U variables make manifest the feature about factorization near poles. So this comes out as a consequence of these non-trivial equations that the U satisfy, the so-called U equations, that tells us that the U of a given curve on a surface plus the product over all the other curves on the surface C prime of their U variables raised to the number of times that these curves C prime intersect C has to be equal to 1. So in the integration domain that we care about the U's, they're all positive. And so from these equations, we see that automatically they all have to leave between 0 and 1. And on top of that, when we go near a pole, then the integral develops a singularity precisely in the region where the respective uij goes to 0. And so from these equations, if a given uij goes to 0, then all the ukm's that corresponds to curves that cross ij have to automatically go to 1, so that this equation is satisfied. This is usually what's called the binary behavior of these U variables. And very nicely, this tells us that in the Kober-Nielsen factor in our amplitude, when we go near this locus where a given uij goes to 0, the contribution coming from all the curves that cross ij has to go to 1. And so automatically, this product factorizes into the product of the curves living on the left times those living on the right, as we expect to happen. Okay, so let me now proceed to explain how, using these formulas, we can derive some new interesting features of the amplitudes. And I'll start by this kinematic connection between these three different colored theories. So once more, Nima already talked about this last year at amplitudes, so I'll also be fairly brief. So the statement is that if you start with this stringy trace phi cube theory and you shift the kinematics by a linear shift that I'm calling delta ij, where delta ij is equal to plus delta if I and j are both even, minus delta if they're both odd, and 0 otherwise, then all that happens in the integral is that we have this extra factor over here that very nicely, when we write the u's in terms of the y's, it highly simplifies into something which is really only changing the integration measure. So for simplicity, this delta shift, all that it's doing is really just changing the integration measure of our integral. And now the claim is that, well, when alpha prime delta is equal to 0 at low energies, of course, I get just trace phi cube theory because this factor disappears. But when I turn it on and I choose it to be just any value that is not an integer, then at low energies, I'll get the NLSM. And finally, when alpha prime delta is precisely equal to 1, I get non-supersymmetric Yang-Mills theory at low energies. Okay, so let me start by explaining how this goes for the simplest case of the NLSM, where we can further consider the limit in which alpha prime delta is also much smaller than 1, so that we can establish the connection between these two theories directly at the level of the field theory amplitudes. So in this case, we just start with field theory trace phi cubed, and we shift the propagators by this delta ij. So here's an example at 4 points. All that this amounts to do is to change the S channel by minus delta here and the T channel with a plus delta. And we can check that when we expand at low energies, so for X is much smaller than delta, then the leading term in this expansion is precisely the NLSM amplitude. Okay, so this is just an example. We have some on-shell ways of understanding why this connection is true, but more broadly, to prove it at all orders, we actually have now a Lagrangian derivation of this connection between trace phi cube theory and the NLSM. So the last point that I would like to emphasize here is that this connection is actually practically useful because, well, the Lagrangian for pions is famously infinite. So if we want to compute amplitudes at higher and higher points, it gets computationally a bit heavy, while the trace phi cubed one is extremely simple. So we can do this for trace phi cubed and then just shift and expand and to get the same objects for the NLSM. Okay, well, let me now proceed to this limiting case where alpha prime delta is equal to 1. So all that happens is that the measure, instead of being a dy over y, becomes a dy over y squared. And now I claim that at low energies, I'm going to get gluons. Okay, so well, the first question one can ask is, how can you get gluons if all this expression depends on is still on dot products of momentum? So where are the polarizations of the gluons? So what this object is really describing is the scattering of colored scalars, but they're crucially coupled to gluons in the standard minimal way. And so if I start with the scattering of these two n scalars, that as I just told you is given by this formula over here, then I can extract n residues, basically, so that I go on the limit where each pair of scalars merges and produces an on-shell gluon. And so by doing this, I can access the gluon amplitude, okay? So this is how we can get gluons out of this formula over here. And this is what we call scalar scaffolded gluons, as each gluon comes from a pair of scalars. And at tree level, we can actually show that this expression precisely matches what we get from bosonic string theory for a particular special choice of polarizations. At loop level, things are a little bit more tricky because the bosonic string answer is fairly complicated. So all that we do is we start with our trace phi cubed loop object, and we literally just change the integration measure from a dy over y to a dy over y squared. And this is what at low energies is going to define surface gluon integrands. One thing that I would like to point out is precisely because now the form that we're integrating is this dy over y squared is slightly harder to actually extract the field theory limit compared to when it's a simple logarithmic form. Nonetheless, there's still a part of the gluon amplitude. Well, in a second, I'll explain how I can get the field theory amplitudes systematically. But from this expression, there's still a part of the amplitude which is extremely simple to obtain, which are called the leading singularities, which is what I get when I put all the internal propagators on shell, which is basically what I get from computing consecutive residues, and I kill off all the integration variables here. So here's an example of the leading singularity of this box diagram. It looks a fairly complicated expression in the x's, fairly long, and this is precisely because this formulation is giving us gluons in general dimensions. If we then further go to 4 dimensions, this actually highly simplifies. Anyway, but in a second, I'll get back to this. Okay, so let me proceed to the second part, where I'll talk about this pattern of factorizations away from poles and the connection to some interesting zeros of both particle and string amplitudes. So I'll just start by stating what the phenomenon is. So the claim is that if I set a special collection of pi's.pj to 0, where crucially I and j are two not adjacent indices, so that I'm not close to a pole, then the amplitude factorizes into the product of two lower point amplitudes. And then if I further set some pi's.pj inside one of the subfactors to 0, I can make it vanish. And so in this way, I can access a 0. Okay, so I'm going to call these factorization splits just so that we don't confuse them to the standard ones that are near poles. Okay, so now what I want to tell you is that we can actually understand these splits has a very simple consequence of basic features about these u variables that enter in the curve integral. So one natural question one can ask is, let's say I have a surface S and a subsurface S1 inside big S. And can I write down the u variables associated to the subsurface S1 in terms of the u variables of the big surface S? Well, it turns out that this question has a very nice answer, which is the following. So if I have a curve little x inside S1, then its u variable can be written in terms of the u's of the big surface as just taking the product over all the ways of extending little x into curves on big S. So here's just in red some possible ways of extending little x into big S. So more technically, we just take the product over all the curves on the surface of their u variables raised to the number of times that little x is contained inside big X. And this is what we call the extension formula. And so having this, to get these split factorizations, all that we need to do is consider two subsurfaces of S such that all the curves in big S belong to either S1 or S2. And the minimal way in which you can do this is by picking the two subsurfaces such that they overlap on a triangle, like I have here. So this is to be contrasted with the standard factorization for which S1 and S2 share a common edge, but precisely the curve corresponding to this common edge does not live in either S1 or S2, so it basically fails to meet the criterion that I just described. But so for these two subsurfaces that I have here, I have their respective curve integrals in terms of the u variables of the subsurfaces and the respective kinematics. And now, using this extension formula that I just told you, I can literally build kinematics for the big surface such that it literally splits into the product of the two subsurfaces. And this can just be done in the following way. So if I start with the integrals that I just gave you, all that I need to do is plug in the expressions for the u variables of the subsurfaces in terms of the u's of the big surface. And by doing this here, I just get a product over curves on the big surface, where now the exponents can be read off as linear combinations on the kinematics of the subsurfaces. Okay, so this linear map follows a very nice graphical rule that I'll explain. So if I take a curve x on the big surface, then under the split kinematics, it maps into the sum of the curves that it decomposes into in the smaller surfaces. So here's an example, this black curve x, you see inside S1, it turns into this little curve x1, and inside S2, it turns into this little curve y2. So that's precisely what it maps to under the split kinematics. And crucially, because I asked for all the curves in the big surface to be contained in either of the subsurfaces, this means that no curve is mapped to 0. And so making manifest that we're factorizing away from poles. Okay, so now from going from these splits to zeros is extremely simple. All that we need to do is consider a split pattern for which one of the subfactors is a 4-point amplitude, because in this case, we know exactly what the amplitude looks like, and we can check that it vanishes each time s plus t is equal to 0, or more generally, any negative integer. And so following this procedure, we can construct a broad class of zeros for both particle and string amplitudes. And both the zeros and the split properties, they have a very nice justification and explanation from the curve integral and these features about u variables. However, a standard physical interpretation, maybe coming from the Lagrangian, is still currently lacking, and it will be very nice to understand. Okay, so just to be more concrete, at tree level, when we go on the split kinematic locus, we're going to end up imposing some linear constraints in the x's. And it turns out that we can reinterpret these constraints as setting a particular pattern of these pi's.pj to 0 for I and j not adjacent. And then we can very nicely conclude that these splits that we're observing are precisely those that were observed a few years ago by Freddy, Nick, and Bruno. And on top of that, of course, you can consecutively split and split and split until the sort of last part where we're just left with a product over 4 points. And this very nicely agrees with this minimal kinematic limit that Bernd just talked in the morning. Okay, but now from the moment that we understand where these splits are coming from these u variables perspective, we can actually generalize them to all orders in the topological expansion. So here's are some examples for splits for the loop integrand. In this case, we have two subsurfaces where both of them have some topology. Another case here is where they overlap on two different triangles, and still there's a split there. And maybe the simplest case is a situation in which one of the subsurfaces has no topology, so it's just a tree-level factor, and the other one contains all the interesting topology. And this particular split will be very relevant in a second, as it will let us access soft limits that then gives us statements about factorization that also hold post-loop integration. Okay, so that's exactly what I'm going to talk about now. So if we take this particular split pattern where S2 is a tree level, then all that we need to do to reach a soft limit is further consider the limit in which the kinematics entering in this tree factor that I'm calling yij's go to 0. And then it's trivial to show that the split kinematics precisely agree with what you get from the case where these particles down here are all going soft. Okay, and so basically this tree factor reduces to a soft factor that pulls out of the loop integration, and so that is the universal soft factor that we get for the amplitude. Well, and so all that I told you about is about the stringy trace phi cube theory, but very nicely we can actually generalize these statements for pions and gluons by just using this delta shift that I told you about. So this relies on a very special feature of the delta shift, which is that it turns out that it is compatible with all the split kinematic constraints imposing to go on this split locus. Okay, but well, we've proven that this is the case, and so all the splits that I just told you about also hold for pions and gluons, and crucially let us access multi-soft limits for both of these theories. And here I'll just summarize what we've concluded for pions. If we send an odd number of pions adjacent to each other soft, then we can show that the amplitude vanishes at all orders. So this is a slight generalization of the Adler zero, which is what we get when we send a single pion soft. But more interestingly, if the even number of pions that we're sending soft that are adjacent to each other, then this limit is actually finite, and we have a soft factor that we can give a closed form expression for, and it has a very nice interpretation in terms of one of these amplitudes in these mixed theories of scalars and pions. Okay, and so this brings me to the last part of my talk in the last 5 minutes, which I'll explain how this curve integral gives us a generalization of kinematics that I'll call surface kinematics that allow us to define perfect integrands for these theories. So it has been a long-standing challenge to determine real-world amplitudes, in particular integrands, exclusively by the knowledge of what happens in single cuts. Okay, so at tree level, this has had large success. All that we need to know is that the amplitude is a rational function, together with the fact that it factorizes into lower points on poles. We find a direction for which it vanishes at infinity, and we can just use BCFW to recursively construct the amplitude. But already here, it's crucially that we go away from strictly Lorentzian kinematics to complex kinematics so that the sort of starting building blocks in these recursions are non-zero, so that the 3-point amplitude doesn't vanish. However, at loop level, if we try to do the same thing, this is automatically not possible, just by the fact that there's a new sort of cut already at one loop, this loop cut where I cut the loop propagator open. And in this case, I would like to match on the right-hand side to something at tree level where I glue two adjacent legs. This is usually what's called the forward limit. And from this side, I'm of course going to have a contribution where these two external legs meet, which is going to give me a 1/0. So this limit is divergent. This doesn't happen in maximally supersymmetric theories because when I sum over the supermultiplet here, it actually turns out to cancel, and so everything goes very smoothly. But for the theories that I'm described, this is a problem, and it's associated with the fact that there's no canonical D-integrand, meaning an object which all cuts have an interpretation in terms of lower objects, okay? And so for pions, it's associated with the fact that I can have an integrand that has the Adler zero directly before loop integration, and similarly for gluons, that it's gauging variant before loop integration. So let me just quickly recast this problem in the surface language. So this sort of loop cut is the cut that I get when I cut my surface open via one of these curves that connects to the puncture. So I get a tree surface on this side. And the divergence comes from the fact that this curve, x11, has to be set to 0 in momentum space. It's the curve corresponding to the tadpole. So here I have something divergence. However, in this curve integral formalism, we are completely free to keep all the curves, even those that don't have any standard momentum meaning. So what I'm saying is I can read off these exponents xc, instead of reading them by homology, as I described at the beginning, I can slightly generalize it and read them by homotopy. Basically saying that for curves like these tadpoles, as well as external bubbles for which a similar issue arises, I can just give them names and keep them in my integral. And by doing this, I'm going to automatically have objects that correctly match on all the cuts. So in particular, we saw that at tree level, we had to generalize kinematics from Lorentzian to complex. And what I'm saying is that at loop level, we need to go further away to what I'm calling surface kinematics, where I think about the kinematic invariance entering my problem as naturally associated to curves on surface. And so by doing this, I can then define the surface integrands for pions and gluons. For pions, we can compute them recursively to all loop orders, very simply by just shifting trace phi cubed. And very nicely, the objects that we get have both the Adler zero as well as all these split properties that I talked about directly at the level of the loop integrand. And for gluons, we have an object where all the single cuts match. And that on top of that is gauge invariant directly at the level of the loop integrand. So let me just make this point a bit more precise. So for gluons, we have an object for which these tree-like cuts match as well as these loop ones. And we can very nicely read off what happens in the cuts directly from the surface picture, where these sort of gluing rules are crucially only defined when we keep all the surface kinematics. So all the curves on the surface, even those that don't have a standard meaning in momentum space. So from the moment we have these objects, we can basically compute them recursively. At tree level and one loop, we find some interesting directions in kinematic space for which they vanish at infinity. And so we can recursively compute them as sum over single cuts. Well, we're still working out the case at higher loops, but in both cases, their objects are manifestly gauge invariant, and they also enjoy all these split properties and multi-solve limits that I just told you about. Okay, so I just want to end with some images. So here's what I get, the sort of expression for the gluon amplitude at 4.3 level. It's a polynomial in these x's, and at 2.1 loop, I here highlighted, sorry, you can't really see very well, but I highlighted some of these variables that don't have meaning in momentum space, but they're all over the place in our integrands, and they're crucial to have something that matches on cuts. Okay, so let me quickly end with some future directions, got it, where, well, a very nice thing that we would like to understand is how can we do fermions in this language. A very nice paper came out in the beginning of this week doing this for colored Yukawa theory that I think Mark will talk about later today. More broadly speaking, it would be nice to understand how to get closer to the realistic particle content of the standard model. And if we want to go to the unexplored territory in this framework of uncolored theories, namely for gravity, it would be very interesting to think about this as now a problem about curves, closed curves on surfaces. Thank you.
Thank you very much, Carolina, for a very interesting talk. Questions?
I was wondering what you have to say about scaffolding for gravitons.
Yeah, so you can, like, just by itself, scaffolding is a pure kinematical trick. So you can definitely do it for gravitons without any problem. And in principle, if you double copied these like scalar scaffolded gluons, you would get scalar scaffolded gravitons in that way. So that's something you can do. But I mean, what I was hinting here at last was a more intrinsic actual closed curve description that was not so double copied motivated. But you can definitely scalar scaffold gravitons.
Do you see why higher spin shouldn't?
No, you can do it for any integer spin.
Okay.
Just not half integer because they don't couple to scalars. Like you can do it for fermions, but for any integer spin you can do it. It's just a kinematic statement.
Oliver?
Yeah, I was wondering what happens if you compare the hidden polarization dependence of the gluons with the traditional CFT way of getting gluon polarization dependence at tree at loop level. Would you, for instance, have new input how to efficiently organize IBPs and all that?
You mean for these gluon integrands, like for this generalization of the kinematics, you mean?
Yes, exactly.
Yeah, well, it's not, you see, you can't do this in the standard like world sheet picture because you're putting in basically a momentum at a time. So when you specify the momentum that are incoming, the sort of momentum of the inner propagators are just automatically determined. So you don't have a flexibility to add in these extra curves. If you do this in standard world sheet theory, I don't know if this is what you're asking, but I'm just saying that these sort of variables that I add that are crucial to like make my integrands have these nice features, they don't have a very nice, like I can't give them momentum interpretation. It's really that they're curves that are dual to propagators, and that if I just give you the information about the external momentum that are entering a given graph, all the momentum of the inner propagators are just locked, right? So for tadpoles, you're forced to have them that they're zero by momentum conservation. But here, since my basic objects are just literally the things that are associated to propagators, I have the freedom to add them back. And so they don't have a standard meaning in momentum space. There's, yes. So I don't know, I can't tell you like they're related to certain polarizations. There's no meaning in terms of those.
Okay, thank you.
Question over there.
So I was wondering if you thought about masses, because it seems that you can very easily interpolate between the massless theories and Higgs theories where the vectors are just massive instead of massless.
Yeah, so I mean, for trace phi cube theory, well, you can give masses in a very simple way. So I mentioned a little bit about these soft limits for that theory. Those are not very interesting for trace phi cube, but they become extremely interesting if you allow massive trace phi cube. There you do have some interesting statements. So in that case, you can give masses. For the other theories, I haven't thought too much about it. Like for the NLSM, I know Carol and collaborators are thinking a little bit about how they can use these shifts to give masses in an interesting way, but I haven't thought too much more about it.
One more question here.
So with regards to the forward limit, when you have this other way of organizing the forward limits, what happens? Does that forward limit go away? How do you organize that for the Yang-Mills theory?
Yeah, let me just say, the thing is that it is no longer a forward limit, because the forward limit is a limit where the tree kinematics is restricted, right? I mean, you have L minus L, and that's the problem. What we're doing by sort of thinking about all the kinematics as these curves on surfaces is that when we go on this cut, we get an object that has completely generic kinematics, because all the curves now have a meaning in the lower point surface. They correspond to the sort of propagators appearing in those diagrams, and we're just keeping them there, not putting any restrictions on them. So it's really a match at generic kinematics, just like what happens when you have tree-level cuts, right? That the two objects on the right and the left side are at generic kinematics. So this is really the generalization that it's happening. That's why it's not possible to give it to all the variables that I have, give it a momentum space interpretation.
So the last question from me. For the splits which are loop-loop, not three-loop, does it mean there is a kinematics when the two loop splits into one loop times one loop?
Yeah, that's a great question, yeah, because I didn't say anything about that because I thought I was going to run out of time. So that's a fantastic question. Let me just go back. So yeah, so these loop-loop splits, right, they all impose constraints on the loop momentum. The sort of split kinematics is imposing some constraints on the loop momentum. So they only hold at the level of the loop integrand. But it's still an interesting question whether these splits actually uniquely determine the integrand, not only for trace phi cube theory, but now more interestingly for gluons and pions.
Okay, thank you. So thanks a lot, Carolina, again, and both Lauren and Bernd from Morning Talks.